ISRO, India's space agency, has recently launched its first satellite to study black holes. The X-ray polarimeter satellite was sent to space aboard ISRO's PSLV rocket. This incredible feat makes India the second nation to study black holes and other space bodies using an orbiting observatory. The new satellite is carrying 2 scientific payloads and is going to study different cosmic sources of X-rays. NASA launched a similar mission in December 2021. It has shed light on the remnants of supernova explosions and particle streams emitted by black holes. As for India's mission, it's expected to last for around 5 years. It's likely to help us understand X-ray emission mechanisms of different astronomical sources, like neutron stars, black holes, and star-forming nebulae. The scientific payloads are supposed to investigate the polarization of intense X-ray sources. It can help us better understand the geometry of such celestial sources and the radiation mechanism. This mission follows a number of successful launches conducted by ISRO in 2023. Those include the Chandrayaan 3 mission that landed a probe on the lunar South Pole and a satellite launched to study the Sun. By the way, the agency has also announced its ambitious plans for 2024, and they include gearing up for the country's first crewed mission to space. The newest ISRO's mission is going to study about 50 potential sources in space, including neutron stars and black holes. So let's talk a bit more about those extreme objects. Both black holes and neutron stars are ultra-dense objects formed from the remnants of stars nearing the end of their lives. First, we'll figure out what a neutron star is. Stars keep their spherical shape because their gigantic mass creates a powerful gravitational field that pulls gas toward the center. At the same time, their cores produce enough energy to prevent this gas from gathering too close to the center. All this creates a nice balance and a beautiful spherical shape. But once a star becomes too old and massive, it doesn't have any fuel left. That's why all the reactions in its core slow down and then stop completely. The star's outer layers try to collapse inward, but they bounce off the core, which remains incredibly dense. That's when everything but the star's core blasts out all over the universe in a bright supernova explosion. But that's not the end of the star. Even without the outer layers, its core keeps collapsing. At one point, the pressure inside becomes so great that electrons and protons melt into each other and form neutrons. The result of this crazy fusion is a neutron star, and 90% of its mass consists of neutrons. It means that the resulting space object just can't be squashed any tighter. Energy starts leaving the fading star, transforming it into a neutron star. A neutron star, which is basically a ginormous nucleus, the central part of an atom, is relatively small. Even though scientists don't know for sure how big neutron stars are, they suppose that these space bodies shouldn't be bigger than 12 miles across. For comparison, our Sun is almost 864,000 miles across. As for black holes, they are probably even more extreme than neutron stars. They pack incredible amounts of mass in a single point, which makes them infinitely dense. And when I say infinitely, I mean it. Such density creates an enormous gravitational pull toward the center of the black hole that no one and nothing, even light, can escape. In other words, black holes are so unique because they're the only existing objects surrounded by a region of space-time that is entirely inaccessible to the rest of the universe. They also heat anything approaching them to billions of degrees F and make it reach the speed of light before swallowing it.
All the planets of the solar system are slowly lining up. Mercury, Venus, Earth, Mars, Jupiter, Saturn, and Neptune are about to form a straight line. This event, called the Parade of Planets, occurs once every 176 years. The last time this happened was almost 40 years ago, and it was a great chance to explore all these planets in one go. On August 20th, 1977, thousands of people gathered outside NASA's Kennedy Space Center. They came to witness the launch of the most ambitious and distant space mission in history. 5, 4, 3, 2, 1, ignition! Launch rocket Titan took off from Earth and left the atmosphere. As soon as the rocket reached outer space, it launched the probe Voyager 2, which began its journey. The probe consisted of a bus 1.5 feet in height and almost 6 feet wide. On top of it, there was a round 12-foot wide antenna. Most of the scientific equipment was mounted on a boom that extended 8 feet outward. On September 5, 1977, Voyager 1, the identical space probe, left our home planet. It sent us pictures of Earth and the Moon. It soon overtook Voyager 2, launched 2 weeks earlier. That's why the second probe has the number 1 in its name. And so the journey through dark space began. March 5th, 1979. About 4 Earth-Sun distances away from our planet, Voyager 1 came close to Jupiter and prepared its scientific equipment to explore the planet. The probe had a dozen gadgets, including a 2-camera system with narrow and wide-angle lenses. So, it could take full-length photos of the planet with the wide-angle camera, as well as close-up photos of specific places on the planet and its satellites. The probe also had a radio science system to determine the atmospheric composition, weight, and gravitational fields of the planets it came across. Infrared and ultraviolet spectrometers could help measure radiation and temperature invisible to the human eye. Various sensors were used to examine cosmic rays. Voyager 1 was the first to find volcanoes outside Earth. Those were on Jupiter's satellite, Io. It has dozens of active volcanoes that constantly spew lava. Then the probe pointed its cameras at the Great Red Spot. That's how people learned that it was a giant cyclone-like storm that hasn't stopped for the entire history of observations of Jupiter. It was also the first time when lightning was detected outside of our home planet. And in the invisible spectrum, Voyager 1 noticed that Io acted like an electrical generator for Jupiter. Ions, which are charged particles, were constantly flying toward the gas giant. This electrical current was 5 million amps. Soon, Voyager 1 continued its journey. 5 months later, Voyager 2 approached Jupiter too. This gas giant has rings around it. They're not like Saturn's though. Jupiter's rings consist mostly of dust. When the planet's rocky satellites collided, they turned into small debris. Gradually, this debris turned into fine dust. Then Voyager 2 approached Europa. This moon is completely covered by a crust of ice, and beneath it, there may be a liquid ocean where life can possibly exist. Voyager 2 was the first to capture the cracks in Europa's ice crust. While flying near Io, Voyager 2 discovered that 6 volcanoes on its surface were still erupting. This meant that the periods of activity of these volcanoes could last for months. Both space probes circled the gas giant several times and then dashed further into space. Such a gravitational maneuver allowed them to gain more speed and saved fuel for the trip. By November 9th, 1980, Voyager 1 had already traveled 8 Earth-Sun distances away from home. The space probe arrived at Saturn. It discovered 3 new satellites of the gas giant: Atlas, Prometheus, and Pandora. This proved the theory that these were the moons that kept the planet's rings in line. It also turned out that unlike Jupiter's, Saturn's rings also contained ice. Voyager 1 took a peek at Titan, Saturn's largest satellite. It's 50% larger than the Moon and even has an atmosphere. It's the only place in the solar system besides Earth where liquid water has been proven to exist. That's why scientists don't deny the possibility of life there. Then it was time for another gravity maneuver. Voyager 1 once again darted away from the planet's orbit. This time, it was aiming upward relative to the line of the parade of planets. Almost a year later, Voyager 2 arrived there. It made a flyby of several of Saturn's icy satellites. Supposedly, a long time ago, these moons collided and knocked huge chunks of ice and rock out of each other. This debris orbited Saturn, collided, and slowly crumbled into dust, consisting of ice and rock. This is how the famous rings of Saturn were born. Another gravity maneuver, and Voyager 2 set off for the next gas giant. 5 years later, it arrived at its destination, 17 Earth-Sun distances away from our planet. For the first time ever, a human-made object approached Uranus. Voyager 2 discovered 11 new moons there. The probe also found that Uranus was the coldest planet in the solar system. Its temperature is negative 350 degrees Fahrenheit. That's 4 times colder than the temperature at the South Pole. At that time, the Deep Space Network was being tested on Earth for the first time. It's a network of radio telescopes all over the planet. They aim at certain points in the sky to establish communication with extremely distant objects. These telescopes have been successfully receiving signals from Voyagers 1 and 2. August 25, 1989. Voyager 2 had already traveled 23 Earth-Sun distances and arrived at Neptune. It was the first time people received images of this blue planet from such a close distance. the probe discovered 6 new moons there, and also took the first pictures of the planet's rings. Engineers then turned off the probe's cameras to save power for its main computer and the instruments that measured the solar and interstellar wind. Voyager 2 left Neptune and headed into deep space. That's why it no longer needed the cameras. A few months later, Voyager 1 sent its last photo back to Earth. It was a family portrait of our entire solar system. Every pale dot was a planet. You can barely recognize Earth in the picture. After that, the camera was turned off to save power. This was the start of the interstellar mission for Voyager 1. For 15 years, Voyager 1 had been flying to the edge of the solar system. On December 16, 2004, the probe passed through the termination shock. This is where the solar wind suddenly slows down and heats up after colliding with the interstellar wind. The space probe managed to endure this test and continued its journey. In 2007, Voyager 2 crossed the same boundary. At that point, sensors recorded a temperature of about 266 degrees Fahrenheit, but the probe managed to withstand it and continued its journey through the dark cosmos. Both Voyagers moved through interstellar space in different directions. They discovered that the heliosphere, the solar wind bubble, is not perfectly round, but more like an egg. August 25, 2012. Voyager 1 became the first human-made object to enter interstellar space. It's now also the most distant artificial object in human history. On November 5, 2018, Voyager 2 also left the solar system. The 2 probes continued their journey into deep space. Right now, the Voyagers have been operational for 44 years. Voyager 1 has traveled 153 Earth-Sun distances and is moving forward at 38,000 miles per hour. In about 300 years, the probes will reach the Oort cloud. This is a hypothetical region around the solar system with nothing but asteroids and blocks of ice. Scientists believe they might reach the nearest stars in the next 40,000 years. Perhaps one day, the Voyagers will enter these star systems and explore unknown worlds. There may be planets there that look like ours. The probes may even be able to find an intelligent civilization there. For this purpose, each Voyager carries a golden record with a message on it. There are 115 images. Among them, there's our number systems, a map of the solar system and pictures of its planets, diagrams of human DNA, portraits of people, and landscapes from Earth. There's also greetings in 55 of Earth's languages, including the oldest and newest of them. There are also 90 minutes of music from every corner of our planet. The Voyagers also carry a device to play these sounds. If another civilization gets this record, their scientists could decode the data step by step. And then, that civilization may decide to pay us a friendly visit. They'll have to repeat the heroic journey of the Voyagers, though. Dozens of light years through dark space. Then crossing the border of the solar system, and finally flying past Neptune, Uranus, Saturn, Jupiter, Mars, and the asteroid belt toward the little blue planet. We can only hope that people will be advanced enough to welcome them.
On August 20th, 1977, the most ambitious space mission took off from Earth. The main goal of Voyager 2 was to study the outer solar system up close. It became possible because of a rare alignment of planets. Voyager 2 was supposed to study all the gas giants of the solar system: Jupiter, Saturn, Uranus, and Neptune. Astronomers also hoped it would be able to find and explore the edge of the solar system. Since Voyager 2 was built for interstellar travel, the probe was equipped with a large 12-foot wide antenna. It allowed the spaceship to send the data it gathered back to Earth. During its journey, the space probe discovered a 14th moon of Jupiter. Voyager 2 was the only spaceship to study all 4 giant planets from up close. It was the first human-made object to fly past Uranus, where it found 2 new rings and 10 new moons. Voyager 2 also flew by Neptune and noticed its great dark spot. That's a colossal spinning storm in the planet's southern hemisphere. The storm is the size of Earth and moves at a speed of 1,500 miles per hour. These winds are the strongest ever recorded on any planet of the solar system. In the history of space exploration, only 5 spacecraft have managed to leave the gravitational pull of the solar system. Those were Pioneer 10 and 11, Voyager 1 and 2, and New Horizons. People launched thousands of objects into space. These objects easily overcome Earth's gravity, but the Sun is around 300,000 times as massive as our home planet. That's why its gravitational pull is way more difficult to fight. Even more impressively, Voyager 2 is the second human-made object in history to reach the space between stars after passing through the heliosphere. That's a bubble of magnetic fields and particles produced by the Sun and protecting the solar system. 2 years after its launch, Voyager 2 started transmitting the first images of Jupiter. The space probe provided scientists with much-needed information about Io and Europa, some of the largest of Jupiter's moons. Then the space mission passed by the gas giant itself. The distance between the spacecraft and the planet was around 400,000 miles. That's when the probe noticed some changes in the shape and color of the Great Red Spot. It's an enormous, long-lived storm system, like a hurricane on Earth, but much, much larger. 2 years later, Voyager 2 reached Saturn. It discovered spokes and kinks in some of the planet's rings. While the spacecraft was flying behind and up past the gas giant, it passed through the plane of Saturn's rings. At that time, Voyager's speed was around 8 miles per second. For several minutes, the probe was hit by thousands of micron-sized grains of dust. This kept shifting the probe's direction, and its control jets had to fire many times to stabilize the vehicle. After Voyager 2 explored Uranus and Neptune, it headed out of the solar system. Its instruments were put in low power to save energy. In August 2007, the spacecraft passed the terminal shock. It's the boundary marking the outer limit of the Sun's influence. Here, the solar wind slows down. In the summer of 2013, the probe reached interstellar space. Now, when it comes to sending and receiving signals in space, there are 3 factors you should keep in mind: distance, power, and time. The farther away a spacecraft is, the farther a signal has to travel before it reaches it, and the longer it takes for this signal to catch up with the spacecraft. And when it finally gets there, it's extremely weak. Another problem is that once the spacecraft is launched, it can't be upgraded. It's literally stuck with the technology it was outfitted with. Plus, such spaceships as Voyager 2 are powered by radioactive fuel. When special material radioactively decays, it releases heat that gets converted into electricity. Unfortunately, the more material decays away, the less power the spacecraft has for receiving and transmitting radio signals. Despite this issue, we haven't lost the connection with Voyager 1 and 2. That's because new and more powerful technologies appear on Earth. Signals people send can reach much farther than before. That's why it was possible to stay in touch with Voyager 2, which entered interstellar space in 2018 and has already traveled almost 12 billion miles away from Earth. But in March 2020, the main piece of equipment that allowed scientists to exchange signals with the spaceship was switched off. After the communication with the spacecraft stopped, NASA spent around 11 months upgrading its deep space network and installing new hardware. The DSN is an international array of huge radio antennas that help astronomers on Earth communicate with interplanetary missions. These antennas are located in California, Madrid, and Canberra. The one used to keep in touch with Voyager 2 is a 230-foot wide dish in Canberra. This is the only equipment that can send commands that can reach the probe. This antenna, known as DSS-43, started operating in 1972, 5 years before Voyager 2 and 1 were launched. At that time, it was only 210 feet across. Since then, the dish has received a lot of repairs and upgrades, but these 11 months were the longest the antenna was offline. In October 2020, the antenna was finally ready for a trial after all the upgrades and repairs. The mission operators sent a set of commands to Voyager 2, and after many months of radio silence, the spacecraft returned the signal. The probe confirmed it had heard the call. After that, the spacecraft carried out the commands. While the dish was offline, the mission operators could actually receive scientific data and health updates from Voyager 2. Astronomers kept getting data from interstellar space, the region outside the Sun's heliosphere, but they couldn't send any commands to the probe since it had traveled too far away from Earth. The upgraded antenna received 2 new radio transmitters, and it was done just in time. One of the transmitters, that was used to communicate with Voyager 2, hadn't been replaced in almost 50 years. The antenna also got new cooling and heating equipment and other electronics necessary to support the advanced transmitters. Now, a curious thing about the Deep Space Network is that its radio antennas are positioned in a very precise way. They're spaced equally around the globe. This way, almost any spacecraft can stay in touch with at least one facility at all times. But Voyager 2 is an exception. In 1989, it made a close flyby of Triton, Neptune's moon. It was the only close encounter people had with the eighth planet of the solar system and its moon. By the way, Triton is the largest known object that is believed to be born in the Kuiper Belt. That's a donut-shaped ring around the Sun full of icy objects. Voyager 2 discovered Neptune's ring system and its tiny inner moons. The probe also gathered a lot of amazing information about Triton. For example, it became clear that the moon is covered in cryovolcanoes. Instead of spewing molten rock, these volcanoes spit ice consisting of water, ammonia, and methane. When the New Horizons spacecraft flew past Pluto more than 25 years later, it discovered the same phenomenon on the dwarf planet. Anyway, to make this detour, Voyager 2 had to travel over the gas giant's North Pole. But this changed the probe's trajectory, deflecting it southward relative to the planes of the planets. Since then, Voyager 2 has been moving in that direction. And now, the spacecraft is so far away that it's out of reach of the radio antennas in the Northern Hemisphere, those in Madrid and California. This makes DSS-43, which is located in the Southern Hemisphere, the only dish powerful enough in broadcasting just the right frequency to send commands to Voyager 2. Voyager 1, the probe's faster-traveling twin, didn't change its trajectory. After passing by Saturn, it took a different path. That's why now it can easily communicate with the two facilities in the Northern Hemisphere. The upgrade the Canberra Deep Space Communication Complex has gone through can also benefit other space missions. For example, the Mars Perseverance rover that landed on the Red Planet on February 18, 2021. The dish will also be crucial for exploring other planets and the Moon. Voyager 1, which has been traveling through interstellar space for more than 45 years and is trailing a long gray beard by this time, not really, it suddenly began to send strange signals to Earth. Even more bizarre, there are no signs that the probe has broken or anything. Scientists from NASA are desperately trying to find the reason. So, what's happened exactly? First of all, let me tell you a bit more about Voyager 1 and its long journey. Voyager 1 is an American space probe. Scientists from NASA sent it into space on September 5, 1977. Voyager's goal was to explore the outer planets of our solar system, namely Jupiter and Saturn. Initially, scientists assumed that the mission would take about 5 years. Haha, the joke's on them. The probe exceeded all expectations. Not only did it fulfill its mission, but it's still working for much longer than expected. Voyager 1 has been wandering around space for more than 45 years. It's hard to estimate what Voyager 1 has done for science. Firstly, it successfully sent a lot of photos of Jupiter and Saturn to Earth. By the way, you can even check out these photos yourself. All of them are published on the NASA website. Thanks to Voyager, we also discovered several new moons of Jupiter and a previously unknown system of its rings. We learned that Jupiter's famous red spot is actually a giant superfast storm. And after leaving Neptune's orbit behind, Voyager also sent a lot of important data about interstellar plasma. So Voyager 1 successfully proved to scientists how useful it was. After that, it happily headed for its next goal, the Kuiper Belt and the heliosphere. The Kuiper Belt is a ring of icy bodies that extends from Neptune to a distance of approximately 50 AU from the Sun. It's kind of similar to the asteroid belt, but about 20 times wider and 100 times heavier. And the heliosphere is an area around the Sun where the pressure of the solar wind is balanced with the pressure of interstellar gas. Yeah, I know, it sounds like some hard scientific stuff. Just keep in mind that this data really helps us understand the universe as a whole. So, this is Voyager's last task, to tell us more about interstellar space. The probe has already sent us more than 60 frames for a mosaic of the solar system from a distance of over 4 billion miles from Earth. Scientists use these frames to make a big colored picture. The photo was called the pale blue dot, and you've probably already guessed what that dot is. Yep, that's what our Earth looks like through Voyager's eyes. This photo clearly shows how tiny we really are and how precious and fragile our planet is. But Voyager 1 also has another, even more important mission: to tell other civilizations about us humans. You might have heard about the famous Voyager Golden Records. People created many audio and video files and added them to these records. There are a few sections. The first one contains hello in 55 languages, including ancient and extinct ones. Almost 80% of the recordings are different musical pieces, like Bach, Beethoven, Mozart, and Stravinsky. Folk music from different countries and ages, and a bit of the blues, like famous songs by Louis Armstrong and Chuck Berry. The remaining 20% of the recordings contain different human voices, sounds of nature and animals, as well as 116 images encoded as audio signals. There's also recordings of speeches by Kurt Waldheim, a former UN Secretary General, and Jimmy Carter, a former US President. These are just some friendly messages. In addition to the records, scientists also packed a needle for playing them. Don't worry, they also left a simple drawing that showed how to use all this stuff and how to translate the sounds into pictures. They added Earth's coordinates, which they created using a pulsar map. It shows the position of the Sun in the Milky Way. The record was packed in an aluminum case and covered with gold to protect it against radiation and cosmic dust. Carrying this record, Voyager 1 set off on its long journey, and it has already traveled quite a distance, I'd say. Right now, Voyager 1 is 154 astronomical units away from us. That's about 14.5 billion miles. This makes it the most remote human-made object. Initially, this title belonged to the Pioneer 10 mission, but Voyager overtook it in 1998. What a bargain for NASA! It's way beyond its best-by date. Voyager 1 is actually so cool that it even overtook its twin brother, Voyager 2, which, by the way, had been sent into space 2 weeks earlier. Voyager 1 moves at a speed of 9.7 miles per second. That's 35,000 miles per hour. Even the fastest sports car in the world travels at a speed of only 305 miles per hour. So it's hard to imagine the speed of Voyager. Anyway, at the moment, Voyager is heading to the borders of the Oort cloud. That's the name of a hypothetical layer of icy objects surrounding the solar system. Astronomers haven't confirmed its existence yet, but they're almost sure it's there. After all, even black holes were only a theory not so long ago. Unfortunately, Voyager 1 won't return back to the solar system. It'll keep in touch with Earth at least until 2025. But eventually, we'll lose the connection with it for good. In 300 years, it'll reach the borders of the Oort cloud. And in 30,000 years, I won't be around then, it'll finally leave the solar system. And if nothing happens to it along the way, in another 10,000 years, Voyager 1 will approach red dwarf star Gliese 445 in the Giraffe constellation. In the future, the probe will probably keep wandering around the Milky Way galaxy. And now, let's finally discuss the mysterious signals part. So, what happened? Well, a rather unusual thing. NASA's Jet Propulsion Laboratory, which monitors and controls both Voyagers, reported this problem in May 2022. Our veteran spacecraft suddenly began sending strange data to Earth. The whole situation puzzles even engineers from NASA. Now, I bet you're thinking, come on, the thing just probably broke down or something. But the truth is that Voyager 1 is totally fine. It works as usual, receives and carries out commands from Earth, and collects and sends scientific data. But the readings of the AACS, which stands for Attitude and Articulation Control Subsystem, don't show what is actually happening to Voyager anymore. This system supports the orientation of the probe in space and helps it keep in touch with Earth. So, basically, the signals mean that the probe's orientation in space is messed up. But scientists claim this is not the case. They know that the source of the antenna signal remains in the same position relative to Earth as planned. The problem hasn't triggered any of the onboard fault protection systems. The probe hasn't even entered safe mode. So, what in the world, or universe, is going on? Suzanne Dodd, the head of the project, says that the problem is not actually that unexpected. After all, Voyager 1 is already 45 years old. The expert admits that what's happening to the probe remains a mystery to them. They don't know exactly where the incorrect data is coming from, and it's unclear how this will affect the operation of Voyager. She adds, though, that it's not that surprising, considering that the probe is in interstellar space. There's a very high level of radiation there. No spacecraft has ever reached that point before. Scientists from NASA say they'll keep closely monitoring the data coming from Voyager 1 until they figure out the problem. If they find it, the management team will try to fix it. Otherwise, the team will have to adapt to the new conditions. It might not be enough just to understand the problem, though. It takes as much as 20 hours and 33 minutes to receive the signal from Voyager, and it takes the same amount of time to respond to it. Well, at least the second spacecraft, Voyager 2, is totally fine, even though it's also currently in interstellar space at a distance of 12 billion miles from Earth. Anyway, we can only wait for news and hope that the problem will be resolved. I actually wonder how much longer can Voyager 1 last? Will it be able to fly to the borders of the Oort cloud in 300 years? What do you think? I'd like to hear your thoughts in the comments.
Black holes are ruthless. They can swallow asteroids, comets, planets, and even stars. But can a black hole consume the entire universe? Almost any black hole was once a massive star that collapsed in on itself and became incredibly dense. Black holes have immense gravitational pull. Even light can't escape their clutches. The idea that a black hole can swallow the universe is based on a common misconception. People often think that black holes work like vacuums, pulling space inside. But that's not the case. Black holes can only swallow stuff that is extremely close, usually space objects venturing into their event horizon. That's a black hole's point of no return. Once you cross this border, there's no escape. The event horizon for a black hole with the mass of our Sun could extend a mere 2 miles. If a tiny black hole had a mass of our planet, its event horizon wouldn't stretch for more than a couple of inches. It would be the size of your thumb, no more. But a black hole's gravity still affects the stars and planets surrounding it. It might make them orbit, just like the black hole at the center of the Milky Way galaxy does. But the hole doesn't swallow them. If our Sun somehow transformed into a black hole with the same mass, which is highly unlikely, Earth wouldn't feel any difference in the gravitational force influencing it. Our planet wouldn't change its orbit or hurtle toward the newly born black hole. Of course, it would get very dark and freezing cold, but being pulled inside a black hole wouldn't be a concern. Plus, most black holes are quite small. A black hole can only swallow a star if the said star is aimed almost directly at the black hole. Theoretically, it might happen. But according to space experts, for the Sun to get swallowed up by a black hole at the center of our home Milky Way galaxy, a truly enormous amount of time would be needed. After all, the star's orbit would need to line up with the black hole in a very precise way. Even the largest black hole in the universe that we know about, a space titan called Ton 618, seems to be near the theoretical limit of how large black holes can grow. This limit is determined by the fact that black holes release tons of radiation while developing. This radiation heats up and ionizes the matter surrounding the black hole, which makes it more difficult for the dust and gas to cool down and fall into the black hole. As a result, it slows down the rate at which the black hole can feed. We can probably say that this self-regulation stops black holes from gobbling down entire galaxies, let alone the whole universe. And we shouldn't forget about the expansion of the universe either. Objects in space move farther apart, which makes it less likely for them to collide or get captured by a black hole. If a black hole were to consume the entire universe, it would require a tremendous shift in the direction in which space seems to be moving. So, you don't need to worry that one day, our whole world will disappear inside a huge, universe-swallowing black hole. Unless, of course, the universe is already inside a black hole. I'm not kidding. There's a theory that we might be living in a black hole. Think about this. What if a black hole already engulfed us long ago? Surprisingly, some physicists deem this theory pretty plausible. For example, Dr. Nikodem Poplawski, a theoretical physicist from Indiana University, states that everything that a black hole swallows may turn into a new universe inside the hole or on the other side of it. So who knows, perhaps our universe used to be quite a different place until it got pulled into a black hole.
Stellar mass and intermediate mass black holes form when huge stars can't support nuclear fusion anymore and collapse, unable to withstand their own gravity. But it's not so clear with supermassive black holes. The mechanism of their formation is still unknown, since there seem to be no stars large enough to directly collapse into such a giant black hole. Nearly every large galaxy has a supermassive black hole at its center, and our Milky Way isn't an exception. We've got Sagittarius A, which is pronounced Sagittarius A star. This space monster is mostly dormant and rarely wakes up to munch on gas and dust, and still, its mass is millions of times that of the Sun. To be precise, almost 4.5 million times. There are still lots of mysteries surrounding this black hole, but one of the most recent discoveries can also be the most exciting. But we'll get there later. Right now, imagine a distance of 14.6 million miles. It's like about 61 distances from Earth to the Moon. That's the diameter of our supermassive black hole. Of course, it will look tiny compared to the Milky Way itself, which is 100,000 light-years wide and 1,000 light-years thick. But it's still impressive. At the same time, Sagittarius A is dwarfed by a disk of gas surrounding it. It extends for a whopping 5 to 30 light-years and occasionally feeds the black hole. When it happens, faint flashes of X-rays are produced. The disk, known as the accretion disk, is also responsible for X-ray emissions triggered by friction. This friction can make the temperatures inside the disk go as high as 18 million degrees F. And now the coolest part, the supermassive black hole at the heart of our galaxy is not just spinning, it's doing so at almost maximum speed, dragging everything close to it along for the ride. Scientists have calculated the rotational speed of Sagittarius A with the help of NASA's Chandra X-ray Observatory. Normally, the spin speed of a black hole is given a value from 0 to 1, with 1 being the highest rotational speed. Speaking of our supermassive black hole, its rotational speed is between 0.84 and 0.96. That's close to the top limit, defined by a black hole's width. Now, the spin of a black hole is very different from that of other space bodies. Solid objects, like planets, moons, or asteroids, have physical surfaces. But black holes are regions of space-time surrounded by an outer, non-physical surface. This surface is called the event horizon, and even light can't escape beyond it. The rotation of a planet or a star depends on the distribution of its mass. At the same time, the rotation of a black hole is governed by its angular momentum. The extreme gravitational forces next to a black hole cause space-time to become slightly curved and twisted. It forms what we know as the ergosphere. This notion is unique to black holes and never occurs around relatively solid space bodies like planets or stars. In other words, when black holes spin, they twist up the very fabric of space-time, dragging along the ergosphere and everything it contains. This phenomenon is known as frame dragging. Come to think of it, the name does make sense. Thanks to this dragging, we can observe weird visual effects around black holes. The theoretical maximum speed of a black hole is determined by how it grows after feeding on matter. As something falls into a black hole, it increases its spin. Plus, we should take into consideration the mass of a black hole. The more massive it is, the higher its gravitational pull is. And this makes it more challenging to increase the speed of the spin. Let me illustrate this idea. Our relatively not-so-heavy supermassive black hole, whose mass is equivalent to around 4.5 million suns, has a spin between 0.84 and 0.96, which is very fast. At the same time, a much heavier supermassive black hole at the heart of galaxy M87, which has a mass of 6.5 billion suns, is spinning just as fast, between 0.89 and 0.91. The solution to this mystery? This black hole is also feeding very rapidly, which allows it to increase its speed.
Black holes are the universe's most enigmatic entities. Their voracious nature lets them devour anything close enough, growing in size with each feast. But what's the range of their sizes? Dive in with me. To give birth to a black hole, you need immense gravitational collapse. Typically, this collapse results from massive stars exhausting their life. Imagine condensing the sun to a mere 1.8-mile diameter, or compressing Earth to pea size. What results? An incredibly dense object with immense gravitational pull, a black hole. While we commonly think of colossal black holes, tiny ones might exist. Known theoretically as primordial black holes, they could be minuscule, down to atomic dimensions. These ancient entities might predate even atoms, originating just post the Big Bang. Back then, with the universe in a tumultuous state, even a slightly denser particle might have become a black hole. These atom-sized black holes might weigh as much as mountains, while those weighing like Earth might only be coin-sized. Though fascinating, their lifespan would be brief due to extreme temperatures making them evaporate swiftly. Our universe houses the known category, stellar black holes. Their mass is often multiple times that of the Sun. For context, the Sun's weight is a mind-boggling number with 30 zeros. The smallest recognized black hole is 2, 4 times the Sun's weight. It drifts through space, hunting for cosmic prey. Gaia BH1 is our nearest neighbor, with 10 times the Sun's mass. At a staggering distance, M33X7, some 3 million light-years away, currently consumes a blue giant far bigger than the Sun. Transitioning to larger ones, we find intermediate mass black holes. They achieve their size by either consuming numerous stars or frequently merging with other black holes. A prominent example weighed 142 solar masses, overshadowing some earthly regions. A pair was recently spotted in a galaxy 17 billion light-years away. Though they'll eventually merge, their current interaction unleashes enormous energy. But the true behemoths in this category are the supermassive black holes. These cosmic giants have masses millions or even billions of times greater than the Sun. The colossal nature of supermassive black holes is baffling. How did they grow so immense in a universe that's only 14 billion years old? Enter quasi-stars, hypothetical stellar titans that dwarf even the largest known stars, like Stephenson 2.18. These could have birthed from the universe's early days, with cores collapsing into black holes even before fully forming. Inside a quasi-star, its newborn black hole would feed on the star's matter, growing larger while maintaining the star's equilibrium. Over millions of years, the black hole would swell, resulting in the supermassive black holes often found at galaxy centers. Contrary to belief, galaxies don't orbit these giants. For instance, our Milky Way's heart houses Sagittarius A, a 4 million solar mass black hole, just 17 times the Sun's size. However, not all black holes are dormant. The one in BL Lacertae gobbles up vast quantities of gas and dust. Then there's the black hole in Messier 87, captured in humanity's first black hole image, capable of swallowing our solar system up to the Orion Belt. But the universe harbors even grander entities, ultramassive black holes. These monsters outshine thousands of galaxies, drawing in everything in their vicinity. OJ 287 Center features one weighing 18 billion solar masses, so vast another black hole orbits it. Lastly, meet TON 618, the universe's largest known object, with a mass surpassing 66 billion suns. Its brightness exceeds 100 trillion stars, illuminating even from 18 billion light-years away. The enigma? We're observing TON 618 from 10 billion years ago. Its current size remains an awe-inspiring mystery, likely magnitudes larger than our last glimpse.
How about going deep, deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding. But there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day?
Black holes are some of the most enigmatic and sinister phenomenon in the universe. They can swallow up entire stars and planets, bending the very fabric of space and time. But what if Earth, our home planet, were to be caught in the grip of a black hole's event horizon? What would we see before the inevitable end? Well, let's have a look-see, okie dokie. So a black hole is like the bully on the playground. You avoid them at all costs. It's a region of space where gravity is so strong that nothing, not even light, can escape it. It's like Houdini in reverse. As with snowflakes, every black hole is unique. Each one has its own mass, spin, and charge. And they also come in different sizes, sort of like jeans. Petite, slim, regular, and husky, or something. Anyway, there are 4 sizes. The smallest black holes are the stellar mass kind. They're born when the massive star runs out of juice and folds in on itself. They're like the chihuahuas of the black hole world. They may be tiny, but they're feisty. They gobble up nearby matter like a hungry puppy. And even the smallest one is 3 times more massive than our Sun. Next up, we have the middle children of this cosmic family, intermediate mass black holes. They're too big to be born out of collapsed stars. Scientists believe that they may be created when several black holes merge into one. And even though they can't dominate galaxies, at least they can swallow up some nearby stars. Goody for them, huh? But do you know who can dominate a galaxy? The enormous monsters of our universe, supermassive black holes. They're the giants with masses ranging from millions to billions of times that of our Sun. And they play a crucial role in the growth and formation of their host galaxies. Finally, there are ultra-massive black holes. Trust me, you can't even imagine the size and mass of these guys. These cosmic eldritch horrors are extremely rare, but the ones we know can devour entire galaxies like Pac-Man. So, what happens if you get too close to a black hole? Or more like, what would you see in your last moments? Well, first, you reach an event horizon. It's like a point of no return, an invisible boundary that marks the edge of a black hole. And here's where things start to get really weird. For example, time starts to slow down. Not for you, for an outsider watching you from a safe distance. If you were falling into a black hole, you wouldn't feel any different. But if you were watching someone else fall into it, you'd see them slow down and eventually freeze in time, like in a paused video. As you get even closer, you would start to see some pretty mind-bending things. The gravity would cause the light around you to bend and distort, creating a sort of funhouse mirror effect. You might even see a halo of light around the black hole, known as the photon ring, or jets of high-energy particles spewing out from the black hole's poles. You can actually get pretty close to a black hole without feeling any major effects. It's only when you cross the event horizon that there's no going back. Your goose is cooked. After crossing this boundary, you'd be unable to see anything. For the person watching you from the outside, it would be as if you had suddenly disappeared. Meanwhile, you might start feeling a bit stretched out, like a piece of spaghetti. This is because the gravity is so stark that it's pulling you in different directions at once. There's even a scientific term for it, called spaghettification. We'll cover linguinification in another video. Now that you're inside a black hole, you're taking aim at the singularity. It's a point of infinite density in its center, where all matter is crushed down to a single point. It's like trying to fit an elephant into a tiny matchbox. Everything gets squished together until it's as small as it can possibly be. Which means it's time to wave goodbye, I guess. And if all that sounds scary, here's another fun fact. Black holes are not rare at all. Actually, there's one in the center of each galaxy, including our own Milky Way. So, does it mean that we'll eventually be sucked into it? And if so, how exactly would it happen? Well, let's see. Imagine a black hole approaching our solar system. At first, it appears as nothing more than a tiny speck in the distance. But as it gets closer and closer, its gravitational pull begins to wreak havoc around. Planets start to veer off course, asteroids are flung into oblivion, and comets are shattered into a million pieces. But just like waiting for the sausage to be served in a German restaurant, the worst is yet to come. Yeah, like that joke. Soon, it inevitably reaches the Earth. First, our planet's atmosphere would be pulled toward the black hole, triggering a massive windstorm. And there'd be huge waves on the oceans, the water itself being distorted by gravitational forces. Imagine seeing seas and oceans getting stretched out. Earth's magnetic field is generated by the motion of molten iron in the planet's core. But now, the extreme tidal forces of the black hole would disrupt this motion, causing the magnetic field to weaken and distort. All this would cause massive earthquakes and volcanic eruptions as the planet's crust and mantle were pulled apart. All infrastructure and technology would be completely destroyed. Buildings, bridges, and roads would be torn apart. Okay, let's hit the pause button. Pretty horrifying, isn't it? Nah, but don't worry. You wouldn't have even seen that much, because you would have felt the effects of the black hole much, much earlier. Well, back to the future. We'll lose our magnetic field even before everything started to collapse. And this means not only that the weather and climate will become terrible, we'll also be exposed to extreme radiation. These gamma rays and the heat from the black hole could drastically change our planet. Say ta-ta to all our beautiful nature. At least misery loves company. We won't be the only ones affected by a black hole, which is probably even worse. As this beast engulfed the entire solar system, it would consume about everything. One immediate effect would be the disruption of the orbits of asteroids, comets, and all the other bodies. The planets would begin to deform and stretch, their surfaces warping like molten metal. The sun itself would be affected, its surface contorting like a glob of putty. And yeah, all this is scary even to imagine. But now, breathe and relax, because none of this will ever happen. This is the bright side, remember? Your infinitesimal odds of winning the big lottery are even better than the Earth ever being swept into a black hole. The nearest black hole to our solar system is called Gaia BH1. Discovered by scientists in 2022, it's found in our own Milky Way galaxy, about 1,600 light-years away from Earth. Gaia BH1 is about 10 times the mass of our Sun, which makes it a stellar mass black hole. It's not very interesting on its own, but its discovery has supplied valuable insights into the behavior of these cosmic monsters. But as you can see, even the closest known black hole is over 1,000 light-years away. They move very slowly, and they'll never get so close to our system to pose some kind of a threat. Hey, but didn't you say there's a black hole in the center of the Milky Way galaxy? Doesn't that mean it's going to eventually hoover up our entire galaxy, you may ask? Maybe not in that voice. Well, don't worry. The correct answer is no. The one in the center of our galaxy is called Sagittarius A star. You may remember it from that viral blurry photo that circled around the internet a few years ago. This black hole is indeed very massive and has a strong gravitational pull, like two 8th graders in love. However, it's still a small beam. It only affects objects that are close to it. The objects in the galaxy are all too big and move too fast to be pulled in by black holes. Nevertheless, they're still fascinating objects to study. Scientists are still trying to unlock the mysteries of black holes. And even though they'll never be dangerous to us, they're still a huge reminder of the incredible power of our universe. Now I think I'll turn my attention to the incredible power of chocolate.
What if the sun, our precious source of light and heat, got swallowed by a black hole? Or even more worrying, what if such a black hole was brewing inside our star right now? Would the sun eventually collapse in on itself, pulling along everything in the solar system? Well, if a medium-sized stellar black hole, formed by the gravitational collapse of a star, swallowed the sun, we would only have around 8 minutes before things went haywire. But if our star swallowed a tiny primordial black hole, we could probably have a chance to survive. The existence of primordial black holes hasn't been confirmed yet. These hypothetical black holes are believed to have formed right after the universe was born. Unlike supermassive or even stellar mass black holes, primordial ones are typically tiny. Their mass is roughly the same as the mass of an asteroid, and their size is no larger than that of a baseball. You can find primordial black holes in a few theoretical models, which have been used in attempts to explain loads of mysterious space stuff, from hypothetical planet X to dark matter. There's actually a theory that primordial black holes could actually be dark matter. If primordial black holes indeed existed, they could appear because some regions of space were hotter, others were cooler, and some areas were extremely dense. Scientists believe these dense spots could collapse into primordial black holes. The most curious thing, though? These holes might be so small exactly because they popped up right after the Big Bang. The thing is, the longer it took a black hole to appear, the larger it was. The mass difference between older, smaller, and younger, bigger black holes was incredible. Compare the mass 1,000 times greater than our sun's and that of a pea. There you go. By now, the smallest primordial black holes have most likely evaporated away, but some bigger ones can still be scattered out there in space. Many theoretical models claim that primordial black holes are so common that it's kinda inevitable for a random star to capture one. Such stars with black holes at their centers are known as Hawking stars. So, what might happen after such an accidental acquisition? At first, a captured primordial black hole isn't likely to have any effect on a sun-like star. After all, compared to our massive star, an asteroid's worth of mass might as well be a speck of dust. The black hole simply isn't able to consume much of the sun, but with time, its persistent presence in the heart of the star can start affecting things. The black hole is likely to begin consuming matter in the stellar core, growing over time. If this process is fast enough on a cosmological scale, the black hole can end up swallowing the star completely. If the process is too slow, it might still influence the development and lifespan of the star. Mostly, it depends on the initial size of the primordial black hole. A large one with around 1/1000th of the solar mass can potentially consume a star in less than 500 million years. If something like that has ever happened, there must be solar mass black holes out there, too small to have been created by supernovae like regular stellar black holes. If the primordial black hole is way smaller, 1/1000th of the solar mass, things might get complicated. This tiny hole will keep munching on the star's core, but at a very slow pace. And still, it will stir things up in the core of the star, making it heat up more than usual. Eventually, the host star will swell into something cooler and redder than usual red giant stars. Plus, the turbulence at its core is likely to affect the surface activity of the star. Since we haven't observed anything like this happening to our sun, it's very unlikely that there's a primordial black hole at its center. But we can't say for sure that there aren't other stars hurtling through space, carrying primordial black holes in their hearts.